In Lecture 11, we're going to take a look at the graphs of the sine and the cosine functions that we introduced in earlier lectures. In particular, we want to be able to identify some of the more important properties of the sine and cosine graphs and look at the amplitude and period of these types of functions, which we will refer to as sinusoidal functions. Then we're going to graph these functions using key points and also look at a general equation for that sinusoidal graph. Alright, so let's begin by looking at this particular sine function right here. F of x is equal to sine of x, and we want to graph using a value table. What I mean by value tables, we're just going to plug in a bunch of values and see what we get out whenever we plug in x. What does y have to equal? And that way we'll be able to graph the curve. Now, in this case, we're going to always assume that x is in radians, unless we are otherwise specifying that we're talking about degrees. Just in terms of mathematics, we almost always stick with radians. Alright, so let's plug in 0. Y equals 0. So remember, whenever we plug in 0 in for sine, if you look at the unit circle definition, 0 is this angle right here. What is the y coordinate of that point? The y coordinate of that point is 0, so sine of 0 is 0. And as we move around the unit circle, looking at different values as we go around, and I'm not going to take us back to that picture, but you've seen the unit circle that we use for definitions of trig functions. We're going to see that as we do pi over 6, that turns out to give us a 1/2 value out for y. If we take sine of pi over 2, that's 1. And what I'm doing is I'm actually just jumping to some of the more interesting points right here. So I looked at this point here, I looked at this point up here. I'm going to look over here at 5 pi over 6 because that gives me a 1/2 also. And then when I get back down to pi, that is going in this direction to the left, that's pi is 180 degrees or 1/2 of a complete rotation. That's going to give me 0. Then if I plug in 7 pi over 6, this is where we begin to drop below the x-axis, so we're down here somewhere. And if you do 7 pi over 6, which is, negative 30 degrees from the negative x-axis, or actually 210 degrees if you go around from the positive x-axis, that gives you a negative 1/2. Right? If we do 3 pi over 2, that's going to give me a negative 1. 3 pi over 2 is, of course, down here at the bottom of that unit circle. And then 11 pi over 6 is going to give me a negative 1/2 as I come back around to over here. And then when I get back to 2 pi, when I've gone all the way around the circle, right back to here, I get 0. Now, what does that look like when we actually put these on an x, y coordinate system? Instead of using the unit circle and looking at just what happens to the y coordinates, what does it happen? What does it look like when we plot x, comma, y all the way down these different points? So at 0 for x, we're at 0. If this is, say, negative 1 and this is positive 1, let's make this full range here 2 pi, which puts pi halfway in between there. And let's do, this is pi over 2, and this is 3 pi over 2. Now at pi over 2, right here, we know we're all the way up at 1, but at, it was pi over 6. Pi over 6 is roughly 30 degrees. Now this is a full 90 degrees here. 30 is only 1/3 of the way here. That's pi over 6 right there. That's already up halfway, right? That's 1/2. It's up to that point right there. And then as we go to, if we make it all the way to pi, right here, we're back down to 0. But 5 pi over 6 is 30 degrees shy, or pi over 6 shy of pi. It's right there. So the first half of this curve looks something like this. It goes up and comes back down. And the next thing that's going to happen is it's going to follow the same kind of pattern here. If we go to 7 pi over 6, we're down halfway. Remember, that's only about 1/3 of the way to 3 pi over 2. We're all the way down here at negative 1. Sorry about that. Get back out of there. And do this at negative 1/2 again, and we're back down to 0. And this thing comes down and comes back up. And there you have the graph of the sine function over the range 0 to 2 pi. Now, because the definition of the trig function comes from the unit circle, if you start at 0 and go around, you end up back here. This is, of course, 0 radians. Oh, you can't see my little 0 right there. That's 0 radians right there. And as you come back around, you get back to 2 pi. Now, what happens is, if you keep going around, you end up back at 4 pi. That's all this angle right here, but you just keep going around and around and around. Now, the reason I point that out is because that means that the trig function, as I go across the x-axis, is going to go from 0 to 2 pi. That's the x value, which in my case is the input. That's the radians. But when you get to 2 pi, you start over. So the graph, which we know goes up and comes back down, goes down and comes back up, is going to repeat itself over and over this way and over that way. Okay? Sorry, that ding was my cell phone. Turn that off. All right, so it's going to repeat itself, which means it's going to be periodic. It's going to go back over. So let's look at a few of the more important properties that we see when we identify the sine function. I'm going to scroll down here. All right, so on page 39, we've still got properties of sine functions. Now, the first thing I want you to notice is that the domain, that is the set of all inputs for a sine function, are all real numbers. That is, you can plug in any angle measure at all, and you'll always have a value. Because of the way that the trig function is defined on the unit circle, you will always have, no matter what angle you choose, you'll always have a y-coordinate for a point on the outside of the unit circle that intersects that angle. Okay. On the other hand, the range of the sine function only goes from -1 to +1, and you can see that up here in this picture. The highest point that it reaches on the y-axis is 1, and the lowest point that it ever reaches is -1. Notice the graphs always stay between -1 and +1, so the range is -1 to +1, any real number between there, because it passes through every possible height between -1 and +1 inclusive. Next, the sine function is what's called an odd function. All right, we talked about odd before. Odd means if you plug in a negative angle, you actually get the negative value of the sine of x. And the way that you can tell that by looking at this picture is that when you go back to the left, it's a mirror image of the curve, but flipped around the x-axis. So, in other words, let me draw another picture down here to illustrate this. If I go this far, and that's x, I have this height right here, right? That's sine of x height. If I go that exact same distance in the negative x direction, guess what's going to happen? I'm going to be exactly the same distance away from the x-axis, only in the negative direction. Okay, that's sine of negative x. It's also the same thing as negative sine of x. As we illustrated earlier, this function is periodic, which means it repeats itself every 2 pi. So after 2 pi goes by, it's going to be back in the same place that it started with. The x-intercepts are negative pi, negative 2 pi, and so on out in the other direction, in the negative direction, and 0 pi, 2 pi, 3 pi. That's where it crosses the x-axis. So it crosses the x-axis here, 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 here. Notice that's every multiple of pi. The y-intercept is 0. So on this picture right here is the y-intercept, because that's where it crosses the y-axis. The maximum value of the function, that is the highest point of the curve, is 1, and the lowest point of the curve is -1. The highest points occur right here, here, and would be right here, and somewhere over here. And those happen at pi over 2, 3 pi over 2, 5 pi over 2, 7 pi over 2. So those are odd multiples of pi over 2, right? Pi, actually not even odd multiples because you got 3 pi, we're skipping. So it's pi, 5 pi over 2, 9 pi over 2. See, that's the pattern you see right there. And same thing is going to be true for the minimum. They occur at all the other multiples or odd multiples of pi over 2. But that just happens to be where those lowest points occur, right? There's a low point here, a low point here, a low point here. But those are some of the important characteristics that we have for our sine function. Now let us walk through the same process with our cosine function. And the distinction now, the difference between what we did before and what we're doing now is that when we look at the unit circle, and we go around the unit circle, we're looking at the x-coordinate for each of these input angles. So if we start at 0, right, the x-coordinate to that point is 1, 0. Which, by the way, I think earlier, you might want to correct this. I wrote 0, 0. That's 1, 0. All right, so with that fixed, let's come back down to here. Alright, so now we've got 1, 0. That means when we plug in 0, we're at 0 angle. Our x-coordinate is 1. So cosine of 0 is 1. Cosine of pi over 3, I'm going to skip over pi over 6 and go straight to pi over 3. And the reason is, if you go to pi over 3, your x-coordinate ends up being 1/2. Right, that's a nice, easy one to graph. I could go ahead and do pi over 6, which is going to give me the square root of 3 over 2 that we learned last time. But I don't want to graph all of them because I'd have to plug square root of 3 over 2 into my calculator and figure out what the decimal value was. And it's just easier. And I'll get enough points by just doing these. If I go straight up to pi over 2, the x-coordinate of that is 0. Right? If I go to 2 pi over 3, the x value of that point is -1/2. And if I go straight out, which is the pi direction, my x-coordinate is -1. Right there, the x-coordinate of that point. And then coming down here, here, and back up, it's going to give me, and you start to see the pattern here, we're going to go back down to -1/2. We're going to go to 3 pi over 2 is going to give me a 0. And then that's going to give me 1/2 and back up to 1. So let's look at this picture. If this is -1 and this is +1 on my y-axis, and on my x-axis, let's go out to 2 pi, which makes this halfway here pi, halfway between 0 and pi is pi over 2, and halfway between pi and 2 pi is 3 pi over 2. Now at 0, x equals 0, my height is 1, so I'm actually up here at this point. At pi, I'm back down to 0, and at 2 pi, is that right? No, I'm 0 here at pi over 2, and I'm down at -1 at pi. I'm back up. Oop, come back. There we go. And then I'm back up here. Now, pi over 3 is very close, or 1/3 of the way, or sorry, 2/3 of the way to pi over 2, right? Because it's actually 1/3 of the way to pi. It has a +1/2. And then if I go right here, which happens to be 2 pi over 3, it's -1/2, right there. This comes back up, which is very close to 3 pi over 2. And then close to 3 pi over 2, I'm also up halfway. And so what you end up with is this wave that looks like this. And what you'll notice is it's actually very similar to the sine function, only it starts in a different place. It goes down and comes back up. Notice exactly how similar it is when you think about what happens because this thing is periodic. Because remember, you're going to keep going around and around and around this circle to get the next values after pi over 2, or if you went before 0, right? We started at 0 and went to 2 pi, but what happens if you go beyond this way or beyond this way? Well, just look at what happens when you expand it. This looks almost like the sine wave, right? Except it's shifted this way. It's a shifted sine wave is what I call that. Because the sine starts right here and goes up and comes back down, right? Which I'll draw here in a second, but I want to go ahead and take a look at that. Couple of properties that you'll see that the cosine function has. By looking at the graph on the previous page, you'll be able to see that we've got a lot of familiar, similar properties for the cosine function that we had for the sine function. For example, the domain is the set of all real numbers. That is, everything, any angle will produce an x-coordinate where the angle intersects the unit circle. Okay, the range also, just like the sine function, ranges from -1 to +1. The lowest point is -1, the highest point is +1. Now, unlike the sine function, the cosine is an even function. What do I mean by even? I mean that if you do cosine of -x, you get exactly the same thing as cosine of x. And you can see that by looking at a picture and how this thing extends from the y-axis. This thing bounces back and forth like this over 2 pi. This thing does the exact mirror image over here. So if I went to, say I went this distance right here, called that x distance, this height right there is cosine of x. On the other hand, if I go the exact same distance -x, I get the same height. Notice these two right here are the same. So that's also cosine of -x. They're equal to each other, which makes it an even function. The cosine function is also periodic, just like the sine function. And you can look at the picture. I'm not going to scroll up, but you can see this easily on the previous page, that the x-intercepts all occur at the odd multiples of pi over 2. Instead of at the multiples of pi, it's at the odd multiples of pi over 2. And by odd, I mean 3, 1, 5, 7, and so forth. -3, -5. Those are all the odd multiples of pi over 2. That's where the x-intercepts are. And of course, the y-intercept is not 0 like it was for the sine function, but it's up here, which means it's 1. The maximum occurs at 1. The minimum occurs, that is the lowest the function ever gets, is -1. And these values you can correspond with what's on the previous graph. You can see that that's where those maximum and minimums occur. To get a little bit better feeling and understanding, familiarity with this curve and the effect of different parameters on the curve, I've got a little web demonstration I'd like you to go and play with, and I'm going to walk through this on the video, but you should do this too. In fact, I encourage you to pause the video here, click, or actually go type in snipurl.com/WBU, and there's an underscore there, underscore trig1, and see if you can't answer these questions right here on your own. What effect does A have on the graph, and what effect does the value omega, which looks like a W, but that's the Greek letter omega, what effect do those have on this graph right here? Sticking a number out in front of the entire function and sticking a number in front of the x inside the function. What effect does that have on the graph? Alright, in this web applet, you're seeing a little bit of a demonstration of how you can explore y equals a sine of omega t. We're going to use these sliders that occur up here at the top of this graph to see the effect that moving or changing the value of a in front of the sine function has an effect on the graph. So what you see here is the sine function. Right? This is actually, if a was 1 and omega was 1. So you have y is equal to sine of t. This is the graph we just saw in our notes. Now, just to look at this a little bit better, I'm going to pull up the whole thing right here in the center of your video. If I come up here and tap and hold on A and drag it to the right, for example, let's drag it to, see if I can get right on 3. There we go. What effect did that have on the graph? Now, I've got still in red the original sine function. However, I now have the black colored curve is y equals 3 sine of x, or in this case f of x is equal to 3 sine of x. What effect did it have? Well, it made it taller, but where are the x-intercepts? Same spot, right? Boom, 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 boom. It's the lowest point and the highest point that changed. What happens if I drag this thing down to 2? The highest point becomes 2, the lowest point becomes negative 2. In effect, it is how high above the x-axis the curve actually now goes. If I go negative, for example, if I go to negative 1, it's hard to get right on there. It's going to go from negative 1 to positive 1, only it goes in the opposite direction of the original sine wave. And if I, of course, go down to negative 2, negative 3, it goes down first instead of up, and the lowest point's negative 3 and the highest point's 3. So just to keep our parameters similar, I'm going to put this back on 1. It's easier said than done with this little pin that I've got. Get on 1. Come on. There we go. Oh, so close. All right, let's try it again. Get up there. All right. Let's just get as close as I can. All right, we'll say that's good enough. What happens to change omega? If I drag it back and forth, you see it has an effect on the width of the graph. Not the height of the graph, but the width of the graph. And the way we'll describe that is actually the frequency of the wave. You've heard of frequency when you talk about your radio wave frequency or the frequency of your monitor. That actually is a very similar concept to this. But what we mean by frequency in this case is how many times does the wave repeat, right? Over, like for example, normally at 1 it would repeat once every 2 pi, but if I change it to 2, it's going to repeat twice every 2 pi. If I change it to 3, it'll do 3 times every 2 pi. Another way to describe it is it has something to do with the wavelength, right? The wavelength is the distance from one tip of the wave to the next tip of the wave. Let's describe some of those things mathematically now. So what effect does A have on the graph? The A has an effect on what I call the amplitude. Actually, what is called the amplitude, not just me, but anybody calls the amplitude. That's the vertical height of the graph. And what effect did omega have on it? It was what we call the frequency, which is another way of describing the period, right? How period or wavelength, which we mean the horizontal length of the wave. Now there's a theorem that relates these two concepts, frequency and period, together. But let's talk about amplitude and period in terms of those values. If omega is a positive number, then the amplitude or height of the wave and period are given by the following formulas. The amplitude is the absolute value of A, and of course when I say vertical height, keep in mind I mean height above the x-axis. Right, so if we're looking at a wave that does this, I don't mean the total height, I mean this right here is the amplitude. That is this distance here, not this distance. That's actually 2 times the amplitude. Okay, and the period is how long does it take for the wave to repeat itself. I'm going to call that t, and you can always find that by taking 2 pi, which is the value whenever omega is 1, right? If you plugged in a 1 here, you'd get just 2 pi. That's the period for the natural sine wave, for the basic sine wave. If omega is higher, then you divide by whatever omega is, and you'll get a new period, which is the length of the wave. According to that previous theorem, we can look at a function like this one, y is equal to 3 sine of 4x, and we see that the a value is 3 and the omega value is 4. We can use that to answer the question of what is the amplitude. Remember, that's the absolute value of a, which in this case would be the absolute value of 3, which gives me just 3. The amplitude of this sine wave is 3. The period, that is how long it takes to repeat the wave, is going to be 2 pi divided by omega, or 2 pi in this case divided by 4. Reduce that fraction, you get pi over 2. That is the length of the wave, how long it takes for the wave to repeat. Now, this information that you get right here is very important because you can use that to now graph any sine wave. Okay, and we're going to use that information that we have to be able to graph these things by hand. So we can describe, just by looking at a graph, we can quickly sketch the graph. Now, here's some 4 steps to go through. What you do is you first find the amplitude to determine the maximum and minimum values of the function. This tells you what the scale for the y-axis is going to be. Then you use the period, which we also know how to calculate, thanks to our previous theorem, and divide the interval that goes from 0 to whatever this period is, which I can call that t. Whatever this value is here, mark that off on your x-axis and divide it into 4 subintervals, and use the endpoints of these intervals to obtain 5 key points on the graph. Now, what do I mean by 5 key points? Well, think about the sine wave. If this is the period, then you know the sine wave is going to start here and end here. Halfway through, it's going to be also back to the middle. Halfway between there, it's going to go up whatever the height of A is and down negative A. And there's your sine wave, but it's dependent on t and A. If you did a cosine function, it would start here, right, come down, back up this way, and this cosine function would look like this, whereas the sine function was the one that was in red. And you can graph each one of them individually just using those 5 key points. Right? Once you've got those 5 key points, then it's simply a matter of connecting the graph, smooth curve, right, and then extend the graph in each direction. So, make it keep going off in each direction. All right, so let me do a couple of examples of how we would graph those. Let's consider graphing y equals 3 sine of 4x by hand. All right, now to do this, I need to know the amplitude, which will be the absolute value of a. In this case, that's the absolute value of 3, or 3. I need to know the period. T is equal to 2 pi over omega, or 2 pi over 4, which becomes pi over 2. Now, to graph this by hand, remember, we start with the interval 0 to whatever t is, in this case, pi over 2. All right, so let's draw my x and y axis. The height of my curve is determined by this number. So here's 1, 2, 3, and it's going to go down -3. And let's go out to pi over 2. So you take that interval and you divide it into 4 equal pieces. Now all you got to do to figure out what these are is divide this by 4, right? Because you got 4 subintervals. So pi over 2 divided by 4 is actually pi over 8. So that's pi over 8 right here. This would be 2 pi over 8, which is pi over 4, and this is 3 pi over 8, because that's 3 of these lengths of pi over 8. Now, sorry about that. Let's jump back up. All right, so if I go, since it's a sine wave, it's going to go from 0 up to the highest point, back down to the lowest point, sorry, back down to the middle, back down to the lowest point, and back up. So then you connect this with a smooth curve. Right, if you go another pi over 2, let's go the same distance again to here. 2 of those are going to be pi. It's going to repeat itself. Go up and down and back. Up and down and back. If I went the same distance over here, it's going to go down, back up, and boom, like that. So there's your graph of 3 sine of 4x. Just like that. That's all there is to it. Now we go through the same process one more time. Let's identify the amplitude, which is the absolute value of A. In this case will be 2. Let's do the period. I need a little bit of algebra here. 2 pi over omega is going to be 2 pi over. Now we got a problem. What's the problem? You remember the theorem I showed you? Go back up to the previous page. This statement right here. Okay? Period's always going to be positive because it's a length of the wave. So omega had to be 0. Had to be greater than 0. What happens if it's not greater than 0? Alright, see that case right here? You've got the negative sign sitting right there. Well, guess what? I'm going to erase what I just did and show you what we do is we take advantage of a property we've seen before, namely this property right here. Okay? In particular, this formula for the fact that sine of negative x is equal to negative sine of x. Pull the negative outside, and then we don't even have to worry about the omega being negative. Right, so go here to rewrite this as the negative sign gets to come out front of a sine function. Because it's odd, you can always pull negatives outside the front of a sine function. Y is then going to be equal to negative 2 sine of pi over 2x. So now what's the amplitude? It's the absolute value of not negative 2, but, sorry, not positive 2, but negative 2. But still, amplitude is still going to give me 2. Right? And the period is going to be 2 pi over 2. Now if you invert and multiply, 2 pi now times 2 over pi gives me a period of 4. So let's go and look at what this graph looks like. So here's your x-axis, here's your y-axis. The height is 2, and it goes down to negative 2. We're going to go from 0 to 4 and look at this interval. So let's go 1, 2, 3, 4. Now the nice thing about this one is, well, now you easily know what the 4 pieces of the graph are. Namely 1, 2, 3, 4. You gotta be careful of one more thing, and that's that minus sign that's out front. Do you remember when we saw what happens? We were looking at this URL right here. Whenever I dragged A to be negative, it flipped the wave. Sorry, hope I'm not making you too dizzy by scrolling back and forth up here. But if there's a negative sign, if negative, go down first. That is, flip across the x-axis. So instead of going up to positive 2, I'm going to go down to negative 2, back up, and then up to positive and down. And I know I'm starting at 0 because I'm working with a sine function. So go down and back up. And then repeat that over and over that way. And there's your graph. Got it? I hope so. Again, the key steps that make this one different is when you have a negative inside on a sine, you can pull it out. If it had been cosine, you just drop the negative because it's an even function, and cosine of negative x is cosine of x. Now, because the negative sign was out front, that meant that we, from the 0 point, went down first and then went up after that. All right, let's do a cosine function now. Let's go ahead and do this one. Amplitude is going to be absolute value of negative 4. I don't have to worry about pulling a negative out because omega is already positive. That gives me 4 for the amplitude. And the period, 2 pi over omega, is 2 pi over pi, or 2. Here's the x, here's the y. Our height is 4, 1, 2, 3, 4. Our depth is negative 4. Our period is 2, so let's go 1, 2. Well, that's going to be a pretty sharp wave. I'm going to spread that out a little bit. Let's try drawing my x-axis again. Boom, boom, boom. There we go. And let's make that 1. Let's make that 2, which means I need 4 pieces. So I'm going to do a 1/2 and a 3/2 right there. Now, because we're cosine, we're going to not start at the origin. We start either at the highest point or the lowest point. And because it's negative out front, we're going to start at negative 4. All right, because it's the flip. Remember, if the amplitude is negative, you flip the wave. Normally, a cosine wave looks like this, right? But if we want to do a negative cosine wave, we got to go start down here and go up this way. So we're going to start here, go up to 0, go up to 1, back down to 0, back down to negative 1. Or actually up to 4, back down to negative 4. By the way, keep in mind, this is not like a parabola. Whenever you hit the highest point and the lowest points, it's actually going horizontal again because it's changing directions. So try to make them flat at the top of these waves. Oops, that didn't look very good. Let's try that again. There we go. And then repeat it like that. There's your wave. The last thing that you can do is you can actually go back the other direction now, right? You can actually, if you know what the wave looks like, that is from the wave, figure out the amplitude and the period, you can come back and write down what is y equals a sine of omega x. Can we figure out a and omega from this picture? And the answer is yes, because you could look at the fact that this thing goes from negative 3 to the positive 3. That means the amplitude is 3, so we know absolute value of a is equal to 3. Now, a could be positive, a could be negative. Oops, sorry about that. And the way that you know that a is positive is because of the fact that it starts at a positive value, and this is a cosine function. If it had started at a negative value, it would have been a negative 3. You would know that from the fact that it starts down here at the negative. Now you know it's a cosine function because it starts on the wave, not at 0. Did not start there. If it had started there, it would have been a sine function. All right. Now what about the period? We know 2 pi over omega has to equal the length of this wave. That is, from the same point on the wave to the next point that's at the same place, the same height. That distance is going to give me the period. In this case, that has to equal 1. So you've got a little equation here. You just solve for omega. If you move the omega to the other side, you get 2 pi, and that is by multiplying both sides by omega. 2 pi is equal to omega, so we know omega is 2 pi. So plug those two values in up here, and you'll have y is equal to 3. You know it's a cosine. And you've got 2 pi x inside. And there you go.